Welcome back to SM219, day 29. Today we'll be talking about the variability of the sample average. The central limit theorem tells us that the sample means are normally distributed, or bell-shaped, if the sample size is reasonably large. The expected value of the sample means is equal to the population average, and that's the way that we'll estimate the population average. We'll use our sample mean to estimate the population average in general. But that just gives us a point estimate. It would be much better to have a sense of the variability of this point estimate. And to do that, we need to understand the variability of the sample means. The variability of the sample means is determined by the standard deviation of the population and also by the sample size. In this first video, we will examine the precise relationship between the variability of the sample mean and the size of the sample. In the second video, we'll use this relationship to determine the sample size that's necessary to give us a desired accuracy. Along with the center, the spread helps identify exactly which normal curve is the distribution of the sample average. The variability of the sample average helps us measure how accurate the sample average is as an estimate of the population average. And if we want a specified level of accuracy, understanding the variability of the sample mean helps us work out how large our sample has to be. Let's move to the class demonstration IPython notebook. You can download your version from day 29. Here's the day 29 lecture demo. First, of course, import the various packages by running this cell. And then to try to understand the variability of the sample average, we'll return to the United summer 2015 data. This is data on flight delays for United Airlines in the summer of 2015. You can see that some of the delays are very long. Delays are measured in minutes here, so this flight to Honolulu was delayed almost 4 hours, whereas other flights left early, signaled by a negative flight delay. Here's a histogram of the flight delays, and you can see this histogram is not bell-shaped. It's far from bell-shaped. It's got a very long right tail, so this is a highly skewed distribution. All the same, the mean and the standard deviation of the delays give a rough sense of the center and the spread of the distribution. They really, unfortunately, don't tell you much about the shape of the distribution at all. You can use the np-mean and the np-std commands to compute the mean and standard deviation of the United flight delays. And we find that the average or mean delay is about 16.65 minutes, and the standard deviation of the flights is just under 40 minutes. Now we'd like to take a sample of size 400 and use that to estimate the flight delays. If I was to do this with one sample, I'd take a sample of size 400, I'd calculate its average, and I'd say that's my best guess for the average or the mean of the flight delays for the whole population of United Airlines flights in 2015. But of course, if I took a different sample of size 400, I might get a different value for my estimate. So it would be helpful for us to take many, many samples and try to understand how these sample average estimates, how these sample averages vary. Here we'll take 10,000 samples and we'll store them in a list or an array called means 400. And so 10,000 times we're taking a sample of size 400. from the United table, and then we're calculating the mean of those 400 flight delays and adding that into our list. Here's what the distribution of sample sizes looks like. These are the estimates. These are the sample sizes, sample averages, and these each would be an estimate for the population average. Population average for all United flights is 16.65 minutes, and you can see here the variability of our estimates. They seem to range from somewhere around 12 to somewhere around 22. Any number between 12 and 22 seems like it's a possible number that we could have produced here. And so we've got a fair bit of variability in our sample averages. Notice that the center of this sample average here sits right about here, about 16 and maybe a little bit more. And so the center, the expected value, let's say, of the sample averages seems to be very, very close to the population average. And in fact, that's true. They're nearly identical. The average of these 10,000 different size 400 sample averages is 16.66 as opposed to 16.65. So, so it's a pretty accurate, or maybe I should say it's an unbiased estimate of the population average. The central limit theorem says roughly that as the number of observations in a sample gets larger, the distribution of the sample averages becomes bell-shaped with the same mean as the population mean. And that's what we've just observed in this previous example. Moreover, the function describing the bell-shaped curve can be written down explicitly. We won't actually write that function down very often, but it's helpful to know. That function depends on the population mean for the center of the bell-shaped distribution, and it also depends on the spread of the sample averages. And the spread of the sample averages is determined by both the population standard deviation, the spread of the values in the population, and also it depends on the sample size for the width of the bell. It depends on the sample size. Yeah. So whereas the mean of the bell-shaped distribution doesn't depend on the sample size, the width of the bell-shaped distribution does depend on the sample size. And the sample size doesn't have to be that large. Here we took sample sizes of size 400, but sometimes you can take them of size between 30 and 60 and still see this bell-shaped behavior of the sample averages. Okay, how does the sample mean vary? In order to show how the variability of the sample average depends on the sample size, that is on how the width of the bell-shaped histogram depends on the sample size, we're going to redo our analysis of the United flights with a larger sample size of size 900. So here's that same code as before, producing 10,000 sample averages, but this time the sample averages are going to be with 900 samples from the United flight data as opposed to 400 size samples. And when you do that, you produce this histogram. And here I've overlaid the two histograms. The gold histogram is representing the 10,000 sample averages of sample size 900, and the blue histogram is the 10,000 sample averages with sample size 400. And what we see is that the larger sample size corresponds to a narrower bell shape. We could encapsulate this process of sampling 10,000 times with a fixed sample size in a function that produces a histogram of the sample averages and a variety of data about the population, about the distribution of sample averages. So here's that function. I don't really need you to know all the details about this function, but when we when we apply this function here to size 100 samples, we get a bell-shaped histogram, mostly bell-shaped. It's got a bit of a right tail, but it's mostly bell-shaped. And you can see that the average of the sample means here, the average of the 10,000 sample means is 16.68, which is pretty close to the population mean, as we expected. But more importantly, what I want you to notice is that the population standard deviation was 40 minutes, and the sample means has a standard deviation of around 4 minutes. It's about a tenth of the width that the whole population had. And that 1/10 is related to this sample size of 100. What if we used sample size 400? Well, we just call the function again with 400, and we'd produce a histogram like this. Again, we get this bell-shaped distribution, and again, the sample mean is very close to the population mean. So that's exactly what we were expecting. But this time, the population standard deviation has shrunk again, but it's shrunk down to almost 2. And when we compare 2 against 40, we compare the standard deviation of the sample means to the standard deviation of the population, we see that the standard deviation of the sample means is about 1/20th of the size of the population standard deviation. And 1/20th is related to this 400 as well. Could even do this one more time with sample size 625, and again, what I want you to observe is that the standard deviation of the sample means now is about 1/25th of the population standard deviation. Increasing the sample size doesn't seem to make any difference in our ability to estimate the population mean using the mean of sample averages. But it seems as if there's an inverse square root law operating with respect to the standard deviation of the sample averages. The standard deviation of the sample averages seems to be about the population standard deviation divided by the square root of the sample size. That's what we've seen in the last couple examples. Here's a second simulation with different sample sizes that shows very close agreement in our predictions. It really is true that the standard deviation of the sample averages is approximately the population standard deviation divided by the square root of the sample size. Here's a table of the sample sizes, the standard deviation of 10,000 sample means for those sample sizes, and the population standard deviation divided by the square root of the sample size. And these numbers should agree to a fairly high accuracy. And if we were to plot the standard deviations, both the standard deviation of the 10,000 sample means and also the population standard deviation divided by the square root of the sample size, we can see almost perfect agreement in the chart here. So this tells us how the variability of the sample means behaves. It tells us that the sample means have a standard deviation, which seems to be about the population standard deviation divided by the square root of the sample size.